People still trickling in, so I'll stall for time. Did I just blow your mind? Oops, this is wet. Why is this wet? I'm gonna get a non-wet piece of chalk. Okay, hi everyone, welcome back. I think, okay, it's 9:02, so hopefully that's been enough buffer time. Just finishing up the first topic. We've been going a little slow because you guys are interactive, but that's great. I love it. Keep the questions coming. So what we've been talking about, kind of towards the end of my lecture yesterday, is kind of what happens when stars leave the main sequence. So first they're on the main sequence, and in the core, you're kind of taking 4 protons and making helium. I don't know why I started calling them hydrogen atoms over here, but please forgive the notational inconsistency, right? So once you run out of protons or hydrogen atoms in this core, you now have this kind of inert core of helium-4. At some point when it's contracting, by the way, it does become degenerate, which people don't often know, okay? But again, you heat up this outer layer, so you're kind of able to sustain nuclear reactions in this shell around the core, and this core keeps growing because as you progressively run out of hydrogen in these shells, you can move progressively outwards. Then eventually, right, this is the helium flash, where you have this triple alpha process happening. Okay, that's when you kind of go to the horizontal branch, and then eventually you do run out of helium in the core, and you end up with this core made of carbon. Okay, so this is a schematic of what we talked about yesterday. And then one of two things can happen. Okay, so I'll draw some arrows. So either if the star mass is lighter than, say, around 8 solar masses, okay, then basically you blow off these puffy outer layers because of the low surface gravity. So they kind of leave, how do I want to draw this? Kind of get, this is the planetary nebula, so this stuff is leaving. And this is the white dwarf that remains. And it's mainly comprised of carbon and oxygen. Okay? So again, per what we discussed yesterday, just giving a really brief recap. Where were we? Oops, that's not what I want. I want this. Right, so as we discussed yesterday, once you have a white dwarf, it's a really simple system. The whole thing is, to good approximation, just one temperature, because it's able to do conduction. And its cooling is really simple. For most of the range of luminosities of the white dwarf, you just have surface photon cooling. But you also have this fun standard model process, is plasmon decay into paraneutrinos. And it agrees pretty well between measurement and our stellar evolution codes. I believe this curve was drawn with Basti stellar evolution code. But over here in this kind of intermediate range, you see there's a few data points where it seems like there could be some channel with excess cooling. So if you ever see some kind of plot that says cooling hint, that's probably what it's referring to. Okay, but then there's other fun stuff you can do with white dwarfs. Here's a couple of examples that I think are really fun and pretty recent. So this, I want to kind of maybe give you a few jumping off points into kind of like the more recent literature, because this is like a really active area. Two ideas here that I'm highlighting. Okay, so over here, there's this really fun idea where if you have a white dwarf, okay, and it's emitting some unpolarized light, all right, there could be an ambient B field surrounding the white dwarf, all right? And like we talked about, axions couple to B fields. Okay, it's like axion, Lagrangian has axion times E dot B. So if there's an ambient B field, you can convert an axion into a photon. So, and again, it's E dot B, right? So the direction that the B field is pointing actually really matters. Okay, so when you have this unpolarized light moving through this B field, if axions exist, then one of the polarizations can actually convert to axions, okay? So then the light's coming to our telescope, but some of the light from one of the polarizations is missing because it's been converted into axions. And so when we observe the light, it looks a little bit polarized, okay, which is not something that we expect from white dwarfs. And so given the non-observation of polarized light from white dwarfs, we can actually set a constraint on the existence of axions. Pretty cool. Here's another example that I think is fun. So in white dwarfs, again, you can kind of make axions and have them emerge from the white dwarf. Again, even though the white dwarf is super, super dense, the axion is really weakly coupled to it. So it just kind of streams out. But then again, it can encounter a B field, and it can then convert back into a photon. Okay, so now we're talking about a segue between making it and then subsequently breaking it, right? So we made it, we broke it. And when you convert back to a photon, you can then try to look for that, okay? So again, due to the non-observation, you can actually set some limits. Now the limit comes actually on the product between GAEE, the coupling to electrons, because you need that coupling in order to make the axion. And then you need GA gamma gamma to convert back to a photon. So the constraint you can set is on the product of that coupling. The two are perfectly degenerate in this situation. And so the way that you interpret that depends on your model of the axion. Okay? So that's a cool example. But OK, so that's not the only thing that can happen, because in the event that your mass is greater than around 8 solar masses, God, I'm a notoriously kind of a bad drawer, so we'll see how this goes. But we kind of get this onion skin model. OK, yeah, I've run out of space, so thoughts and prayers for you guys trying to read anything I write in here. But basically, you can burn iron, or you make iron in the center. You got some silicon, some neon, oxygen, carbon, helium, hydrogen. Yeah, thoughts and prayers to try to be able to read that. I have a better version in the notes that I'm going to post.
Should one of those H's be an Ag?
Yes, thank you. Very good. Should be a helium. Very good. So what's happening with this onion skin, it's basically just a repeat of what we saw in the earlier stages. So you have some fuel that you're burning in the center of the star where it's the hottest. You run out of that fuel. Then it becomes inert. It starts to contract gravitationally, which heats it up. Eventually, you come to a hotter temperature where then you can start to do a new, more energetically demanding nuclear reaction, and you can start to, burn stuff again. But this stops with iron, because iron is the most tightly bound atomic nucleus that we have. So it's the most tightly bound nucleus. Why is that? I don't know. I'm not a nuclear physicist. Ask a nuclear physicist. But that's just the facts of life. I don't even think nuclear physicists necessarily know the answer to that. Maybe yes, maybe no. Yes?
I just had read an astrophysical. I think I've heard different things for different people, but are there some stars that stop somewhere else in between iron and carbon, like stop at oxygen or silicon or neon?
I don't know.
Okay.
Yeah, I don't know. That's definitely not in the textbooks, so it may be possible theoretically, but I don't know.
Okay.
Yeah. OK. Oh, question here.
For both of these steps, you're like doubling or tripling the atomic number, but then there's like from carbon to oxygen, then to neon, you're only changing it by a little bit. So is there something up with that?
Oh, yeah, that's just, if you're, the question is, why is it that for some of the steps you're like doubling the atomic number, but for others it's more incremental? And it's just a question of like what you're combining with. So in the case of carbon becoming oxygen, it's just combining with a helium-4 nucleus. Yeah. OK. So anyway, yeah, this whole sequence can't go past iron. Iron is the most tightly bound atomic nucleus, which means that it actually takes energy if you want to either break iron apart into lighter nuclei, or if you want to make a heavier nucleus out of iron, you have to put energy in order to be able to do that. So once you get to this stage, by the way, this is all happening super quickly by this stage, because the hotter and hotter it's getting, the faster and faster this is all going. I think it's about there. About there. Yes. So here's what happens. And again, this is story time. OK? So you have a super high T. And then what that leads to is a super high number density of photons. The number density scale is like T cubed, very steep power law. So you have a lot of photons. And that means that you have a lot of photons in the high energy tail of the distribution. So photons in the tail can actually break apart the iron. OK? So this is called iron photodisassociation. Photodisassociation. Disassociation. Trying to avoid a repeat of what happened the other day where I misspelled the word walk. OK, and that's on YouTube forever. So trying to avoid that. Yeah, you guys, it ain't easy being up at the board. You know, you kind of lose track of basic things. Okay, so this is iron photodissociation. And as I just said, it actually takes energy to break apart iron. So what that does is that uses energy. So it uses energy that would otherwise potentially be used to kind of hold the thing up against the force of gravity. All right. Also, okay, you have processes like this start to become efficient. So electron and proton can become a neutron and an electron neutrino. And this is becoming efficient. And of course, neutrinos have a long mean free path, so they get to just leave the star. So these carry away energy. All right. And so both of these channels mean you lose energy from the system, which means you have a loss of support. Which leads to collapse, which again leads to higher T, higher temperature. And this whole thing started with a high temperature, actually. So the cycle then is going to repeat, and it becomes actually a runaway process. Okay, so you get a runaway. All right. So eventually, you have this runaway process going on. It's accelerating, and at some point, this has to stop. And so if the core mass is less than around 2 to 3 solar masses, we get a neutron star. Sorry, that's an N, not an H. Neutron star. Otherwise, we get a black hole. Okay? So here's a cartoon illustrating what I just said. So you have the core. It's collapsing because of these two channels of energy loss. And so the upper layers, they lose support while the core is collapsing. So they just kind of start to fall in, okay? But if you're in a situation where you get a neutron star, so when your core mass, your core is supported by degeneracy pressure, okay, what happens is the upper layers, they just kind of fall in and they hit that and they have nowhere to go, so they kind of bounce out, and that releases a ton of thermal energy. So this is called a core collapse supernova specifically. Okay, you have other types of supernova, like type 1a is one that you guys may have heard of. We actually think that one has more to do with accretion disks and white dwarfs, okay, but this is a core collapse supernova. And because of processes like this one, actually most of the energy is carried away, not in the form of light, but in the form of neutrinos. So here's the really classic example that BSM people love to look at. This is supernova 1987A, which occurred in the LMC, which is around 50 kiloparsecs away. Okay, here's some 2 optical images before and after the supernova. So you can see it is indeed very luminous when it comes to photons. However, again, 99% of the energy that's emitted by this thing is in the form of neutrinos. So neutrino experiments actually saw a burst of 20 neutrinos, which, for anyone who knows about neutrinos, that's a lot of neutrinos. I think snow, up in Canada was seeing like on the order of a few solar neutrinos per week. Okay, so to see 20 in kind of one burst like that, especially from a source that's 50 kiloparsec away, right? That is like an insane number of neutrinos. And also, what was interesting is that the neutrinos preceded the light by a few hours because, again, the mean free path of the neutrinos is long, whereas the mean free path of the photons coming out of the supernova, that had a short mean free path, so it had to do this random walk in order to come out, okay? So just like how we've been comparing BSM to neutrinos via the Rafelt criterion, we can do the same thing here again with supernovae. So here's like a really super famous reference over here. It's actually quite recent, but I think this one already has like 500 citations or something, which are just doing a careful job of trying to set limits on the existence of new particles, which could potentially cool the supernova faster than one is observed. Okay? And in this case, it is truly cooling because the ejecta are not virialized. Okay? Sorry, I'm being so pedantic about that point, but this is really my pet peeve. Okay? All right, so anyway, here are a bunch of different plots showing the constraints you can set with the supernova. This one is for if you have particles. Let's say you have Dirac fermions coupled to a dark photon that's kinetically mixed. Here's the parameter space if the particle that's charged on the dark photon is a little bit heavier than the dark photon. Okay, this is then what the parameter space looks like. This epsilon is the kinetic mixing, and they've also assumed something about the dark charge of the dark fermion. Here's the same plot, except in the limit where the dark fermion is lighter than the dark photon. Okay, and here's the millicharge case, where the dark photon is ultra light. Okay, so if the dark photon is ultra light, by dimensional analysis, it looks like it's just charged under the photon. Okay, so all of these three curves, what they have in common is that they're coming down to 10 to the minus 9, so maybe not as good as what you can do with a regular star, actually. But on the flip side, you're going up to much heavier masses because the tails of the distribution of these particles can go up to like 100 MeV, so that's really helpful. But also what all of these have in common is that there's actually a ceiling, and that ceiling corresponds to if you raise the charge or the coupling too much, then these particles are actually going to get trapped by the ejecta, so they're not actually going to cool the ejecta efficiently. Yeah, question over here?
So is the idea here that you have a BSM particle that is being produced during the star's lifetime, but it can't leave due to the mean free path, but then during the supernova it gets like all ejected and you can see
No. So yeah, crucially, so yeah, again, I want to draw your attention to this mass. This is like 100 MeV. So that's way heavier than what you can access just kinematically, given the kinematics of a regular star. So the temperatures in a regular star are not going to be high enough to be able to access these.
This is really produced during the...
That's right. That's right. Yes. Okay. That's right. Yeah, these are progenitor masses and different modeling choices. Supernova, it's kind of a thorny thing to try to simulate. We actually don't have like full 3D simulations of what's really happening. So what these folks did was they tried to be pretty conservative and not not exceed the energy loss to neutrinos, even including like the large uncertainties on what that energy loss is. All right, but yeah, these are just different models, and this dashed line is like this old reference from the year 2000, which just did this kind of more order of magnitude style. So this work was a big improvement in terms of the accuracy and in terms of the parameter space that was accessible.
So it seems that compared to the previous estimate, they mostly improved the upability in the sense that I think that's because I guess the trapping is more difficult to simulate and was not done.
Yeah, that's right. So these folks, to my knowledge, didn't do any simulations, but it's more just doing a more careful treatment of that. Yes. Yeah, question over here.
On the bottom on the right, what's the deal with the two?
Oh, I'm going to come to that in just a moment. Yeah. Was there a question here? No. I thought I saw another question. No, I must have imagined it. Okay, so coming over here. This work, so this kind of lime green blob is qualitatively very similar to what's happening over here, except this is axions now. But yeah, as was just asked about, you have this extra little caret coming out over here. So this is, again, we're transitioning from making it to breaking it, all right? So down here, you can make it, okay? it's not a large enough charge where you're really efficiently cooling the supernova. Okay, you're not cooling the ejecta very quickly, so you don't have this style of limit applying down here. However, what can happen is that you emit these axions, and then at some later point, they can convert back to a photon, actually. Like if they see an ambient magnetic field somewhere, they can convert back. And you can look for those conversion byproducts. So you can look for very, very energetic photons, with X-ray telescopes. And that's where this limit comes from. Okay. I'll also note there's this cosmology limit that they included down here in gray. And it's quite sensitive to the reheat temperature of the universe. So this gray blob, I would say, is quite model dependent. This is a little bit more, well, you made the axion in this situation, so we don't have to care about what happened before. All right? Yeah, question over here.
The extra darker green blob on the left, it also says 1987.
Yeah, good. This is just, I think it's a continuation of this. It's just a different regime. Yeah. Good. All right. What more do I want to say about this? Yes, there's more super cool stuff you can do with neutron stars. Again, this is like a super active area going on. So these are some references from 2021, 2023, 2024. Definitely not exhaustive by any means, but I'm just trying to curate and highlight some that I think are pretty interesting, that are recent. If you really want to get super hardcore and really roll up your sleeves and get in the mud, you can really start to try to work with the simulation. So here's the simulation snapshot from MHD simulations of neutron star magnetospheres, which are really extreme places with very, very high magnetic fields. And so what Ani Prabhu proposed in his 2021 paper was that schematically, if you have the polar regions where you have a large unscreened E field and a B field, then the E dot B can pop axions out, okay? And then those axions, again, long mean free path, they can propagate out. And it's also possible that they can then later convert back into a photon, which you can then look for, okay? And so then in this work, they actually did the analysis and actually looked for it. And this is the limit that they set on the existence of axions, which is pretty cool. And you can also do the same thing. So again, you can have, from the polar regions, you can have these axions coming out. And you can actually think about, trying to look for these axions in your lab. Okay, so if you have a pulsar that's rotating, so pulsar is just a neutron star that's rotating, okay, then if you are emitting axions out of this polar region, the polar region's only facing you some of the time. So it's like a lighthouse where sometimes the axions are beaming towards you. And so you're sending these pulses of axions, and you can then try to look for those axions in your lab, and you'll see a very specific frequency in terms of the pulses of axions corresponding to the frequency of the pulsar. Okay, so that's another cool application of this idea. It relies on you having a pretty good terrestrial experiment to try to actually directly detect those pulses of axions. So here are some different projections for that. Pretty cool. Let's see, do I have more to say about this? Okay, yes. Now we're kind of like, okay, that's the segue. So now it's more story time. That's kind of a segue into talking about looking for these particles in labs on Earth. Okay, so now moving away from this whole story I told you here, we also have the sun, which is a star that's very nearby, obviously. So we can actually use its proximity to our advantage if we want to try to directly detect stuff in the lab. The most famous example of this is CAST. This is the CERN Axion Solar Telescope. So again, you have some process going on in the sun. You make an axion. Okay, the axion has a long mean free path. It streams out of the sun, and it comes to your lab on Earth, where if you've set up kind of this tube where you have this Bohr magnet, a really, really strong magnetic field, you can then convert that axion back into a photon. And now the typical temperature inside the sun is around a keV. So if you're producing really light axions with masses that are much lighter than that, then their characteristic energy just on dimensional grounds is going to be of order a keV. And so what you're going to want is an X-ray detector that can pick up those keV scale X-rays. Okay, and so that's how CAST works. It's sitting kind of up here, so it's not quite as sensitive as some of these other probes. However, what it does have going for it is I think it's like very, very well controlled in terms of like systematics, whereas some of these things over here have a lot of astrophysical uncertainties. For example, I mean, like the pulsar thing I just told you about, this is this lime green area over here. I mean, that relies on having accurate simulations of what's happening around a pulsar and the magnetohydrodynamics, which are really, really hard to capture. So, you know, let's say your favorite axion model lives right here, then maybe you're going to try and argue like, oh, I don't think I believe these pulsar guys. You know, maybe you're cranky and your favorite axion model is the only thing keeping you going, right? But it's going to be really hard to wiggle out of this one, okay? All right, coming over here, this is a related idea. These folks were looking for dark photons coming from the sun. So again, same idea. You have some process in the sun making dark photons. The dark photons come out. And given the kind of energy thresholds that are relevant for experiments like Xenon 110, which are looking for dark matter, if you have a dark photon coming into your lab with sort of keV scale energies, these kinds of experiments can actually absorb those dark photons in a way that, you know, you have to use a little bit of thermal field theory. So you have to, you know, cut some diagrams and do some, you know, detailed balance or whatever. Okay, it's not too bad, but that's how you actually compute the absorption rate within a material like xenon. Okay, and so what these folks were able to do was to recast the xenon limits on absorption of particles and recast it onto the existence of dark photons. So again, xenon is an experiment meant to look for dark matter. These dark photons are not necessarily the dark matter. This is a search for any state in the spectrum of the theory. Okay, so these are the lines if you have a Struckelberg mass. Someone was asking me some days ago about Struckelberg versus Higgs. So here's one difference in how it can manifest. Okay. And then I think maybe this is the last thing I wanted to mention about these ideas. Not to embarrass you, Ken, but Ken had this really, really nice idea some years ago, which is the following. So if you look at the profile of escape velocities inside the sun, what you find is that the escape velocity is around, you know, maybe 0.5% the speed of light. Okay, so generally when you're making these particles in the sun, right, at sort of keV temperatures, and if the particle is light, then most of the time it's going to be going really fast, quasi-relativistically, so with a speed that's much, much greater than this, you know, puny escape velocity. But a tiny fraction of the time, okay, so in some little sliver of the phase space, you are going to actually produce the particles, and they are going to be going with a speed that's less than the escape velocity of the sun. And now you might think, well, okay, but that's really phase space suppressed. That's like a tiny fraction of the particles that get made. However, the particles that leave the sun, they just leave. Whereas these particles that are bound to the sun, they actually stick around and can potentially persist for kind of like order billion years, okay? And so, you know, again, this is a cumulative thing. You get to wait 1 billion years and you get to fill up, he called it the solar basin, so you can kind of think of it as every star has a little puffy cloud or a little basin of particles around it, okay? It's a pretty steep fall off. I think it's r to the -4, if I recall correctly, Ken. And so yeah, the Earth, obviously this is not to scale, but the Earth might be living inside of this little basin of particles, and so that might also be another way of detecting them in the lab. And these particles can have very different kinematics, so that might make them harder to detect because they're going slow, but their density can exceed the density of the unbound particles, so that's helpful. Here are a couple of applications of this idea. Here are some constraints that Ken and Robert set on the existence of dark photons that are kinetically mixed. Okay, so you may recall I showed you a similar looking plot a couple days ago, and I was like, oh, I got to email Kieran. So maybe I'll email Kieran and tell him to add this line as well, because this actually also comes from kind of a recasting of terrestrial experiments, which again, were not designed to look for this, but just by happenstance, they can actually look for this. Okay, and here's a similar idea. So this solar basin little caret down here represents if you have a solar basin of millicharged particles, this is what you can detect in the lab with a technique called direct deflection. Question here.
sharp or whatever slow particles produced, wouldn't they mostly be clustered right outside the sun's surface?
Yeah, you can compute the density profile. It goes like r to the -4. So, yep, it falls off. But it's not 0 at the Earth. Yeah. Was there another question? Okay, I keep like imagining questions. Okay, so I think that's pretty much all I wanted to say about the segue between making it and breaking it. And now I'm just going to focus purely on breaking it, okay, for the remainder of the lecture today. All right? And for this kind of module of my lectures, we're going to talk about galaxies in the intergalactic medium. Okay? There's a lot that's been written about this topic. For me, personally, I really like Tracy Slatcher's TOSI notes because these are the TOSI notes that she lectured when I was a student at TOSI. So for me, it's a little bit like, you know, your mom's spaghetti. You know, you kind of get exposed the first time, and that's what you latch onto. So this is my mom's spaghetti. All right, and where are my notes? Here they are. So we're going to talk about dark matter now. So far in all of these lectures, we've just been talking about particles that exist as states in the spectrum, but now we're going to specifically talk about dark matter. Okay. So we're going to talk about annihilating and decaying dark matter. And now with dark matter, you know, because we have it in the initial state, okay, that's actually what's providing the energy, okay? So as opposed to what we were just talking about, we were talking about pretty light particles, right? And that was by necessity of the kinematics of having to have enough energy to make these particles in an astrophysical system. Now we have dark matter is already there, so there's already energy stored in its mass. Okay, so we can actually now start to talk about going and probing things at higher energies. All right. So, okay, dark matter needs to be stable because we see it today. Okay. But does the stability have to be exact? Okay. So does it need to be exactly stable? All right. So I'm going to just invoke, I know that Tian already gave you some really nice lectures about dark matter, so I'm just going to invoke a number that I saw from her notes that she derived for you, which is the fact that WIMPs have an annihilation cross-section, so sigma v annihilation, on the order of 10 to the minus 26 centimeters cubed per second. Okay, and this is assuming an S-wave cross-section. So in other words, a cross-section where sigma v doesn't depend on the velocity. All right, and the rate of annihilations per unit volume is going to go like sigma v times the number density squared of the dark matter. There's a twiddle there because maybe there's some factors of 2, and if you want to count Dirac fermions or Majorana, identical, whatever. Order of magnitude style, we don't care about that. Okay, so, and again, this is n chi squared. Okay, so this is a rate per volume. We know that it's got to be squared, right? Because for these two particles to kind of find each other, right? If you think about n as kind of like a probability, then you have to like square the probability to like have the particles being in the same place in order to interact, right? That's kind of a heuristic, okay? So if that's how this rate scales, then you know, using a fixed mass density, so for a fixed mass density, which is like the mass times the number density, that means that my rate is going to scale like 1 over the mass squared. Right? So just, moving this mass to the other side and sticking it in there. Okay? Or conversely, if you want to think about the amount of power generated by these annihilations, and the amount of power is proportional to the mass of these particles, so you get 1 power of mass, but it's not enough to cancel the m chi squared down here. So the amount of power scales like 1 over mass. Okay? What that's telling you is that there's potentially a pretty good opportunity to search for dark matter particles annihilating at lower masses. So let's say you want to look at WIMPs, that's telling you that, okay, maybe TeV is going to be really hard, but maybe tens of GeV is going to be more doable, all right? Okay, so let's talk about a TeV scale WIMP. So let's plug in some numbers. All right, we're going to go to Wolfram alpha again. I'm going to try to make it bigger. There we go. All right, so this is just something I happen to remember, that the local density of dark matter is about 0.01 solar masses per parsec cubed. I just happen to remember that. You can also put in 0.3 GeV per centimeter cubed, and then you have to stick in some extra factors of c squared, which I didn't feel like doing. So, okay, so that's the mass density, right? Solar masses per parsec cubed. So now to get the number density, I got to take that and I got to divide it by a TeV. 1 TeV, and I got to remember to put the c squareds in the right place. So let's see, does that give me the right units? Yes, it does. So, and that agrees with what I have in my notes. And remember, 3 equals 10. So the number density is like 10 to the 3 per, what is it, centimeter cubed? Meter cubed. Yes, good. That agrees with what I have in my notes. Per meter cubed. All right. So plugging that in. So I'm going to square that. And I'm going to multiply it times the cross-section that Tian derived for you guys. So that's 10 to the minus 26 centimeters cubed per second. And let's see. Yep, that agrees with what I have in my notes too. So that means that the rate per volume, sigma v n chi squared, is around 10 to the minus 27 per meter cubed second.
So the cross-section is independent of the mass?
Yep,
Okay.
more or less.
Could you repeat the question?
The question was, is the cross-section independent of the mass? And for WIMPs, the answer is yes. So for that, I will refer you back to Tian's notes. Yeah.
I mean, I'm surprised that it's the heavier, the longer the lifetime, right? The rate is inversely proportional to the mass.
Yeah, and that's really just because, for a fixed mass density, the number density just goes down. That's why.
And the cross-section doesn't depend on
That's right. Yep. All right. So I don't really know how to interpret this number. I can't really grok it. So here's what I'm going to do. So again, this is a rate per unit volume. Okay, so it has dimensions of 1 per volume times time. I'm going to multiply it times a time, and I'm going to compare it to this number density right here. So what time am I going to choose? Well, let's just be really aggressive and ask how much. So our galaxy has not existed for the lifetime of the universe, okay? But let's just say it did. I'm going to multiply this by the lifetime, the age of the universe. So even if we give our galaxy an age of the universe, then yeah, it's about 10 to the minus 9 per meter cubed. So over, the age of the universe, the density of annihilations is around 10 to the minus 9 per meter cubed. And so what this means is that only 1 in a trillion, so 1 in 10 to the 12 dark matter particles, so dark matter WIMPs, annihilate in the local Milky Way. Okay? And so there's no way we're ever going to be able to detect that gravitationally, right? That's not really making any difference in terms of what dark matter is doing dynamically in terms of its gravity. Okay? But what about looking at the annihilation byproducts? Okay, so what about detecting the byproducts? In particular, let's talk about byproducts with a spectrum of, I'm going to call it dN, dE naught. And this is just how many photons I make in a given energy bin. And this naught denotes that this is at the source. Okay? So vis-a-vis byproducts, I'm mainly going to focus on photons. I'm going to be photon-centric. All right? But you can also try to do stuff with neutrinos. I'll show a slide later on about why that's hard. I mean, maybe it's not too surprising that that's going to be hard because they're neutrinos, but I'll quantify that later. All right? So, so we're trying to detect a spectrum of photons with that intrinsic spectrum. So how are we going to do that? We're going to build the best telescope we can and try to look for these photons. So let's assume I have some little chunk dV of dark matter, and that chunk is annihilating. Oh, whoops. Ah, no, I've spoiled my scheme. Okay, I've got to put a line here to remind myself to stop. All right. So I've got this little chunk. It's annihilating. It's sending off photons in every direction. So I'm going to assume that there's no preferred axis for the annihilation. Okay. I'm trying to make sense. Everything's just kind of sloshing around in this gravitational potential of the Milky Way. So there's not really a preferred direction for it. All right. And so all of those photons, I'm going to imagine them punching through an imaginary sphere. Okay. And at the edge of that sphere, I'm going to put my telescope. And I'm going to draw it cartoonishly big. Okay. This is my space telescope. All right. So it's some distance r away. Okay, this is a distance r. And the area of my telescope is going to be A. All right? So I want to ask, how many of these photons can I detect? So the number of photons that I can detect, per energy bin. So maybe my telescope has a lot of different energy bins to it. So in a given bin, per volume dV of dark matter that is annihilating per unit time. Okay, this is what I want to observe. Okay. And so to figure out what that's going to be, well, first of all, I'm going to multiply by my intrinsic source spectrum. Okay, this is my spectrum. And for now, I'm going to assume that the spectrum doesn't undergo any kind of distortion as it travels to my telescope, but we can come back to that later. All right, so that takes care of my dN, dE. What about my volume and my time? Well, I also know from up here, I know that the annihilation rate in my volume is going like n chi squared sigma v, okay? So this is a rate per volume. Okay, so now this thing looks like it has the right dimensions, except I'm vastly overcounting because this would be what I could detect if I had a detector covering this entire imaginary sphere. Okay, but I don't. I only have this little area right here, A. So I pay the penalty for only having that fractional coverage. And that fractional coverage looks like A over 4 pi r squared. So this is the fraction of photons that enter my telescope. Okay? So that's, in a nutshell, kind of all the information I need. But now let's suppose I want to, consider all the decays along a line of sight. So I don't want to just consider this one little volume right here. I want to consider anything that I can see in my telescope. Okay, so I want to consider all the annihilation along a line of sight, which is just the direction you're looking in. So what I'm going to do is I'm going to break up my volume into a radial component where this radius is the distance away from me now, okay, and a angular component d omega, okay, and so schematically that's kind of like, again, here's my telescope, and maybe it has some field of view or some kind of pixel effective point spread function with some angular d omega. Okay, some fraction of the sphere. Yes?
Dimensionally, it makes sense, but we need to add.
Oh, yeah, there's R, yeah, sure, r squared. Thank you. Yes. Good. Yeah, bad lecturer. Dimensional inconsistency, not good. All right. So we're just considering some little sliver. This is R, this is dr. And we want to add up all, oh no, now I've made the drawing kind of bad. Okay, well look, there's a nicer version on the notes that I'll post where I can use different colors. Oh, wait a minute, here I can use different colors. Haha, what a concept. All right, I'm looking for all of this dark matter. So I'm gonna integrate over this entire volume right here. Okay. So now if I do that, so I slap a integral dv on that. So now I'm going to have, oh, sorry, I'm actually just going to integrate over r first, sorry. I have dn, de, dt, d omega that I observe. Some of that stuff isn't affected, so I have again, I have my spectrum, dn de, not, and I have a bunch of terms over here that don't depend on r, so I'm going to factor those out. I've got an a, and I've got the sigma v, I've got a 4 pi, and actually I would much rather write this in terms of rho rather than n, just because rho is something that I can directly measure. Okay, so I'm going to write it in terms of rho. And so when I do that, I'm going to have to stick a factor of m chi squared downstairs. So I'm doing my integral r squared dr. And what's left is I have a rho squared, which can be a function of r, over, there's that r squared down at the bottom. And, ooh, I have different colors. And these cancel. All right. That's great. So if I have some kind of a really diffuse source, okay, like let's say I want to look across the whole sky, then I'm kind of done. But let's suppose actually that, you know, maybe your dark matter that you want to look at is really localized. So maybe you're looking at a dwarf galaxy or something. So like if the dark matter is localized, okay, for example, to a dwarf galaxy, then it also actually makes sense to integrate over this solid angle, right? I only want to look at this little region here. I don't want to look over here. So we're going to integrate over a finite d omega. Okay, and so if I do that, and then rearranging this slightly, then I'm going to actually move the area of my telescope, to the other side for reasons that will make sense in just a moment. So I'm going to write this as 1 on A, dn, dE, dt, observed, equals, again, the dn, dE, the intrinsic one, times sigma v over m chi squared times the integral of that thing right there. So I'm going to move the 4 pi over there as well. So integral rho chi squared of r dr d omega over 4 pi. And so why have I written it in this particular way? Well, it's because one really nice property of doing this type of a search is that all of the different factors factorize, essentially, right? So all the stuff over here that I've grouped like in this term is stuff that happens at the telescope, okay? So all of this stuff on the left-hand side is going to be a function of how big is your telescope, what is its energy resolution, what is the energy range that it's sensitive to, what's the bin size, and so on. This stuff right over here is where the particle physics enters. Okay, both in terms of the mass and cross-section, but also it's the particle physics that determines the intrinsic spectrum. Okay, so like if you have annihilation to, I don't know, taus, okay, that's going to look very different from annihilation into Bs. Okay, just in terms of the spectrum and the shower, the cascade that you get. And then finally, this last term, this is the only stuff that relates to astrophysics. Okay, and it's the astrophysics of the dark matter distribution. And this is related to what's called the J factor. There's some factors of 2 maybe in the definition of the J factor, but we don't care about those. I don't know why it's called the J factor. Does anyone know? Maybe it's buried somewhere in Tracy's TASI notes, but I actually don't know why it's called this. I don't know what J stands for. Okay. But this is a really, really nice way of packaging up this information. Oops, did my computer die? I hope not. Oh, no, good. All right, it's a nice way of packaging up this information just because, if you're a particle physicist and you don't really want to, think about this or this, that's fine. And you can just focus on this, all right? Or maybe you're an astronomer, but you like to talk to dark matter people and do searches for dark matter. So maybe you don't know about this, but then you can try to measure this really, really well, either by building telescopes that can do dynamical measurements of the density of dark matter, or maybe you can do some simulation work. Okay, so and then if you're an instrumentalist, you can focus on this side. Okay, so this is a really nice way of doing the division of labor. Okay. All right, so let's talk about some of the different components of this in a little bit more depth. Oh, question here?
Is the density isotropic? Or
We're going to come to that in just a moment. The question was, is the density isotropic? Sorry, maybe this is a notation thing. So let me put a little vector there. Yeah, good. That's why. I'll put it here too. Other questions? Are we good over here? You good? Yeah? Okay. All right. So let's talk about the particle physics. So the spectrum depends basically on what standard model state that you produce. In the final state. Okay. As far as the total cross-section, right, again, I'm going to just rely on the fact that you guys have seen Tiantian's lectures. So, the physics of WIMPs and what sets the cross-section, that's kind of baked in already. We're not really going to change that. But you can change the spectrum, again, depending on what you annihilate to. Okay, so, chi goes to BB bar, looks different. From a leptonic channel, like chi bar, goes to muons. Actually, muons are by far the most annoying final state, and they're the most difficult to detect. So, damn muons. Who ordered that, right? That's what I said. All right. So, how different? Well, you can actually compute this using an event generator. So you can use something like Pythia, or your favorite event generator, PowHedge, or whatever the other ones. Is Geneva out yet? I don't know. I feel like Christian's been working on that forever. No, it is? Oh, good for him. Mazel. All right. So, so you use Pythia, or you use your favorite event generator, and then you look at the spectrum that comes out, and the spectrum dictates what telescope you want to use. Okay. So here is kind of a menu of the different options. Whoops. Uh-oh. Sorry, I told you I would justify and quantify the statement that neutrinos are really difficult final states. Here's that justification from Carlos and friends. Okay, so here is the thermal relic abundance. Indeed, as someone was asking before, it is very, very constant. It doesn't really depend on the mass very much. There's a little bump here, and that actually comes from the changing G star. Okay, so maybe Lloyd told you guys, maybe Tiantian told you guys, they have this number of effective relativistic degrees of freedom in the thermal bath. Okay, and that can affect the thermodynamics and the expansion of the universe. And so I think this one comes from like the QCD phase transition. There's a little bump here due to G star. If that makes no sense to you, forget about it. Not important. Point is, the thermal relic abundance cross-section is down here. All the neutrino stuff is several orders of magnitude above it. Okay, so neutrinos are really, really difficult final states. And even with some of the forecast future experiments, it's going to be really, really challenging to get down to that thermal relic cross-section. Okay, but as I said, we're being photon-centric, so looking at the menu of options that's available for telescopes. Okay, so let's say you have kind of a TeV or 100 GeV scale thermal WIMP. So okay, let's say you annihilate to, BB bar or something like that. There's going to be some type of hadronic shower and cascade, and the energy that gets stored in that is going to get partitioned into a bunch of different photons, and you're going to have kind of a broad, like sort of soft spectrum. So you might have some photons down here with energies of a few GeVs or tens of GeVs. So you go to this nice theory frontier paper, which I think has this really nice summary plot, and you say, okay, maybe my peak of my spectrum is somewhere here, and oh look, Fermi looks like it's the best telescope in that energy range, so I'm going to use Fermi. Okay? So it just depends on what your spectrum is. Okay, so that's all I'm going to say about the spectrum and the telescope choice. Finally, the J factor. Okay, it's helpful to decide the best targets. To look at. Okay, because as dictated by this equation right here, the sources or the chunks of dark matter that have the highest J factor are going to give me the biggest signal. All right. So as far as how you figure that out, you have to do that integral somehow. So you have to assume some kind of a density profile, which can be informed by measurements. Okay. So usually what we do is we assume a smooth profile, some profile, rho of r. And for example, one profile that people often use is the Navarro-Frank-White profile, NFW profile. And that looks something like this. The density is a function of r. It's like this broken power law. So at really small radii, it's one power law. And then at larger radii, it's a different power law. Okay, over here it's r to the minus 1. Here it's r to the minus 3. And the turnover happens at around some characteristic scale radius. Okay. So if you assume something like an NFW profile, you can then go and try to measure dynamically what would be the parameters of that NFW profile that would be consistent with like observations of stars orbiting around in these potentials, and you can try to figure it out that way. So from doing that, you find that the J factor of dwarf galaxies, J dwarf, can be anywhere from 10 to the 17 to 10 to the 20 GeV squared per centimeter to the 5th power. Okay. And there's a pretty big range here depending on which dwarf galaxy it is that you're talking about. And again, it's really determined by a combination of both the density, okay, so like a denser thing is going to be better, but also you win by being closer as well, right? Meanwhile, the galactic center, so the J factor of the galactic center is around 10 to the 22 GeVs squared per centimeter to the 5th. All right, and this is within 1 degree of the galactic center. All right. So yeah, just taking that information at face value, the galactic center seems like a really great place to try to look for signatures of annihilating dark matter because it has such a high J factor. However, there's also a lot of background in that region just coming from regular astrophysics because it's like the downtown of the galaxy. There's a lot going on, a lot of bars and restaurants and people getting in the way. And right now there's this raging debate where we actually do in fact see an excess of gamma rays coming from the galactic center. And it's really, really difficult to determine whether or not that excess is coming from annihilating dark matter. Okay, so the spectrum of that excess, it's peaked at around a few GeVs, and it's consistent with dark matter annihilating to, I think, BB bar, if I'm not mistaken. But it also kind of resembles the spectrum of millisecond pulsars. Now, we've never detected a millisecond pulsar in the galactic center, but maybe they could be there, and they could just be so faint that we can't individually resolve them. So it's a really, really difficult topic to study. It's hotly debated because the stakes are very, very important, right? If we're actually detecting annihilating dark matter, right, and you want to detect dark matter, it's going to get a little bit, it can get a little bit intense, right? So I'm not going to really weigh in on that, but I'll just note that, for that reason, even though you take a little bit of a hit by going to the dwarf galaxies, doing so is much, much easier to interpret because the dwarf galaxies have very, very few baryons, so there's very, very few backgrounds, okay? All right, so just to show you again what's kind of at stake here. So here's some really nice plots from this paper by Rebecca Lean that I really, really like. Here is, again, the cross-section. This is the annihilation cross-section as a function of mass. Again, here's the WIMP, thermal WIMP line, relatively independent of the mass. You may have gone over this with Tiantian, but just to be super explicit, if you go below this cross-section, you actually overproduce dark matter, because if your cross-section is too low, you're supposed to ride down this Boltzmann curve to deplete your dark matter, and if your cross-section is too low, you don't ride down far enough. Okay, so that's not good. Anything above here is fine. Well, this line is actually the prediction of the correct observed amount of dark matter, but anything above the line is fine. Question back here.
Why is anything above the line fine? Because if it's too high, then shouldn't you roll below the
You do, so then you underproduce. The question is, why is anything above this fine? Because, don't you ride the Boltzmann curve too far down? The answer is yes, but I mean, I can't rule out that a subcomponent of my dark matter is made of WIMPs, right? Yeah. Good. So, okay. And here they've done this really nice analysis. Okay, first of all, maybe Tiantian talked about this. There's this unitarity, partial wave unitarity limit. I think, actually, I prefer to think of it as a perturbativity limit, okay? So you can't really have WIMPs being heavier than, like, I don't know, 100 TeV or so. And down here, what they've done is this analysis where they were really conservative, and this is assuming dark matter decays or annihilates to visible particles. So not neutrinos, but literally anything else. And what they did is kind of like energy bin by energy bin. They said, what is the final state that is the most difficult to observe? And for almost all the energy bins, the answer is muons. Okay, so it's a very good approximation. This is coming from the constraints on muons as a final state. So it's very, very conservative in that sense, this curve that they've drawn here. Here's the same plot, but now it's if you assume annihilation 100% into a particular standard model final state. So yeah, like I said, muons are all the way up here. Muons are the hardest final state to observe. Okay, the hadronic ones and the tau are a little bit easier. Okay. Cool. All right, so, okay, I got like 5 minutes left. I want to say some other caveats. I'll go over here. I want to say some quick caveats to what we just talked about, and then we'll break for coffee. Okay, so some caveats. So first of all, I already kind of hinted at this, but the prompt spectrum that you make right after the dark matter annihilates is not necessarily what you observe. Okay, so prompt spectrum can be distorted. Okay, by a few things. Okay, the most obvious one I think is redshifting. Okay, which is most relevant for extragalactic sources. Okay, that's not too hard to deal with though, because you just take your intrinsic spectrum and you put in the appropriate factors of 1 plus Z. Yes, I am a Z evangelist. All right. I don't know if Matt, I think I'm, as an American, I'm giving you permission to say Z. That's true. Yeah, I'm sneaky that way. All right, so good. That's an easy one to deal with. Another one that's not too difficult is attenuation or scattering. Okay. Which is not such a big deal for GeV gamma rays, but it can be more important for other frequencies. It can also be more important, again, for extragalactic sources that are coming from a long distance. And so you can just stick an e to the minus tau, which is a function of energy and redshift, inside of your J factor and call it a day. Okay, so if you know something about the profile of scatterers or attenuators, you can model that and just stick that in there, no trouble. The most annoying one is to deal with if you have any E plus E minus produced in your final state, either promptly or from showers, then they can do inverse Compton scattering. Where they take like some low energy light, like maybe starlight or something, and then upscatter it into higher energies. And you can also have synchrotron radiation. Because we know there's a B field in the galaxy. Okay. So this is usually relevant for radio. So if you have relativistic electrons in a B field, they usually make radio photons. And this is kind of annoying to account for. However, luckily, some folks have done the hard work for us. So you can account for all of this with tools like, it's a hell of a name, PPPC4DM. ID, which stands for the Poor Particle Physicist Cookbook for Dark Matter Indirect Detection. Really rolls off the tongue, doesn't it? All right, so these folks have done the hard work of accounting for these effects, and so you can just stand on the shoulders of giants and use that to account for the signal that you want to look for. My final caveat that I want to say is that for the J factor, we need to compute rho squared. And the way that we have done that, is to assume a smooth